Welcome to the course on error control coding and introduction to linear block codes. Today we are going to talk about how to decode, and we are going to talk about what is known as syndrome decoding. So what is a decoding problem? So let us look at a scenario where we are transmitting our code word, which is n bit tuple, over a communication channel, and let us consider a binary symmetric channel. So in a binary symmetric channel, bits zeros and ones are transmitted over this communication channel, and with probability 1 minus p they are received correctly, and with crossover probability of p the bits zeros and ones can get flipped. So the output of the channel is also binary. Then we have total 2k code words, right? And if we are looking at output receive sequence, we can have total of 2 to the power n different possibilities, because our code word is n bit, and each location can be zeros or ones. So our decoding problem is we have to partition these 2n possibilities into sets of 2k into 2k sets. So we have to map these 2n possibilities into set 2k sets, and corresponding to each set there should be only one unique code word. In other words, when we map a receive sequence to a particular set, we should be able to say if these set of receive sequence are obtained, or we get these receive sequence, then corresponding to these receive sequence there is only one code word. So the decoding problem is we have to partition these 2n different possibilities into total 2k sets, such that in each of the set there is only one valid code word. So whenever any of these receive sequence is mapped to a particular set, then we should be able to say, okay, if you receive any of these sequences, then the transmitted code word was this. So you can think of, we have total 2n possibilities, and we want to partition these 2n possibilities into 2 to the power k different balls in some sense, and each ball has one code word associated with it. That is basically our decoding problem. So how do we partition these 2n different possibilities into 2k sets is what we are going to talk about. So any decoding scheme is basically to partition these 2n possible code words, received code words, into 2k disjoint subsets. The word disjoint is important because we don't want basically overlapping decision sets regions. Okay. And how do we do this partition is basically based on the structure of the linear block code, and that is what we are going to describe in this lecture. So let us denote the 2k code words by v1, v2, v3, v2k, v2 raised to power k. So let us say these are my 2k code words in a linear block code, nk linear block code, where v1 is all 0 code word. Now what do we do is we form an array of vectors from vector space Vn as follows. In the top row of this array, we will arrange all of these 2k code words, with all 0 code word being the leftmost entry in the row. So we are going in the first row of this array, we are going to put all 0 code word, and then we are going to put the other code words. So this will be the first row of this array. Now, suppose we have formed, now I am going to tell you how we are going to form this array. Suppose let us say we have already formed j minus 1 rows of this array, then what do? We choose a vector E j from vector space V n. So, we pick up a n bit error vector which has not been chosen previously in any of the previous j minus 1 rows. We pick that error vector. Next, we form the jth row by adding that error vector to each of the code words on the top row and placing the new vector which is E j plus V I under the code word V I. I will just explain what I mean by this. So, as I said, in the first row we have listed all the code words with all 0 code word as my leftmost entry. Now, let us say I have already formed some rows and I want to form jth row. So, how do I find jth row? I will pick up an error vector E j, which is let us say this E 3, which has not appeared before. So, E 3 should not be any of these elements which have already been chosen. E 3 should not have appeared in the previous rows of this array. So, I choose such a error vector and then what do is I add this error vector to each of these elements in the first row which is nothing but code words, and I place that element under the same column. Now, what do I mean by that? So, let us say this was V 2. So, I will add E 3 to V 2 and I will add the element E 3 plus V 2 in the same column as V 2 was. Similarly, if I have a code word V I, I will add E 3 to V I and I will add this element E 3 plus V I in the same column as V I. So, this is how I am going to build up this row in this array. The next row, how do I build up? Again I will pick an error pattern which has not happened before. I will pick up that error pattern and then I will add that error pattern to V 2, put that element here. Add that error pattern to V I, put that pattern here. So, this is how I will fill up the entries in this array. So, that is what I meant. Form the jth row by adding E j to each of these code words in the top row and placing E j plus V I under the same column as V I. And we will continue doing this until all n bit vectors have been put in this standard array. And this array formed in this way is known as standard array. So, this is how your standard array will look like. Again I just recap how we are constructing the standard array. The first row of this array is set of code words V 1 to V 2 raised to power k, and the leftmost entry here is all 0 code word. Next we pick up an element, an error vector which has not happened in any of the previous rows, and then we add that error vector to each of the elements of these code words and put the new element under the same column as that code word, and we continue doing that until we have put all the possible vectors in this array. So, let us look at a 6-3 linear block code whose generator matrix is given here. Now, how do I find its standard array? So, as I said, the first step involved is you need to write down all possible code words. Now, you have already been given the generator matrix for this code. So, you can find out what are the possible code words. You just have to do V is nothing but U times G. So, there are total 8 code words, and you can find those 8 code words because you know the G is given to you and you know what is your U. U is basically goes from 0 0 0 to 0 0 1 0 1 0 goes to 1 1 1. So, you can find out what these code words are, and I have listed these code words here. So, you have one all 0 code word, and then you have the other code words are 0 1 1 1 0 0, 1 0 1 0 1 0, 1 1 0 0 1 0 0 0 1. Since I could not fit in all the columns in one slide, I have continued it here. So, this is I had up to V0, I have V1, V2, V3, V4, and then I had V5, V6, V7, V8. So, these are my 8 code words for this 6-3 linear block code. Now, how do I find entries in the next column? As I said, I have to pick up a vector which has not appeared in the previous rows. So, let us look at what has appeared in the previous row. We had all 0 sequence here, we had a sequence which has 3 ones, a sequence which has 3 ones, sequence which has 3 ones, code word 4 ones. So, we see we do not have n tuples which have just weight 1, Hamming weight 1, they have not appeared so far. So, this 1 0 0 0 0 0 has not appeared so far in the first row of this array. So, I pick this 1 0 0 0 0 as my first element. Now, how do I find this element? I am going to add this to this. So, I am going to add this to this. If I add it, what do I get? 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 0 is 0. So, this is what I get. How do I get this entry? Again, I add this to this. So, 1 plus 1 is 0, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0. So, this is how I populate the entries in this row. Next, how do I pick this? I will now have to look at the first 2 rows of this array and see, pick one n tuple which has not happened before, and this particular n tuple you can see 0 1 and all zeros. It has not appeared so far in the first 2 rows of the standard array. So, I can then pick this as my n tuple here, and then I fill up this whole entry. How? I add this vector to this V2, put it here, add this vector to this, put it here, add this vector to this, put it here, add this vector to this, put it here, add this vector to this. You can just verify one such entry. So, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 0 is 0, and 0 plus 1 is 1. So, this is how you populate this entry, and we will keep on doing it until we have written all those n tuples here. So, we have already written this way, we have written all the 2n possibilities, we have written it in this array. Now, this array has some interesting properties, and we are going to talk about that, which we will make use of while decoding our linear block code. Every vector in this standard array appears exactly once. This is not very difficult to prove. This follows from the way we are constructing our standard array. Okay. And the proof is by contradiction. So, I will just, it is a very small proof, so I can just give you that. Let us say, so how does the proof by contradiction work? We will assume something and then we will show that our assumption is wrong. That is not possible. Okay. So, we have to prove that every element here is basically unique. So, let us say that is not true. Let us say two elements, let us just call it this element and this element. Let us say these two elements are same. Okay. If these two elements are same, then we can write this as e to raised to power n minus k plus v 2 to be equal to e 3 plus v I, correct. Now, we can write this e 2 n minus k as e 3 plus v I plus v 2. Why? Because these are all binary words. So, basically when we add 1 plus 1, that is basically 0. So, we added v 2 to both the sides. So, v 2 plus v 2 will be 0. So, we can write this error pattern as e 3 plus v I plus v 2. And what is v I plus v 2? v I plus v 2 is another code word. Why? Because that is a property of the linear code word, linear block code. So, this will be e 3 plus some other code word, let us call it v I hat. So, this error pattern e 2 n minus k is e 3 plus v hat. Now, e 3 plus v I hat, this should be in the row containing e 3, because these are, how do we find the entries in the row containing e 3? We add all code words to e 3 and that is what these entries are. So, e 3 plus v I hat should have been some entry here. What does that mean? That means we made a mistake in selecting this error pattern. Note what did we say? We are choosing these error patterns in such a way that in the previous rows this error pattern has not appeared. But here we have shown if these two elements would have been same, if these two vectors in the standard array would have been same, then this is the condition, which would mean that this error pattern is already there in the row containing e 3. So, that means we cannot choose that as our error pattern here, because we can only choose an error pattern which has not appeared beforehand. So, in other words, we are contradicting ourselves. On one hand, we are saying we are picking up these error patterns such a way that they have not appeared in the previous rows, but if we are saying the two elements in this array are same, then this is not possible. So, hence by contradiction basically we prove that this is not possible. We could not choose e 2 n minus k as this, because this has already appeared. Hence, this condition that these two elements are same is incorrect. Okay. So, all the elements of this standard array are distinct and they appear exactly once. No two vectors in the same row are identical. Again, this is very easy to prove because all code words are distinct. So, elements in one row will all be distinct. We call each row of this standard array as coset, and the leftmost entry of each coset or row is known as coset leader, and we have total 2 raised to power n minus k such cosets. Now, the question is, can we make any other element as our coset leader? So, if you just go back here, let us say look at this row, coset leader was this, right, the leftmost entry in the standard array. Now, what happens if we, instead of choosing this as a coset leader, if we had chosen, let us say, this as coset leader, would it have changed our elements of this array? No. Why? If you go back and see the entries of a particular row, here the coset leader was E3. If instead of E3 we would have used E3 plus V2, what would have happened? This would have been E3 plus V2, this would have been E3 plus V2 plus V2. So, this would be E3, this would be E3 plus V2 plus Vi, and V2 plus Vi would be another code word Vi hat. So, this would have been some other code word. So, the elements in each row would have remained the same, only they would have just got reordered. Okay. So, if we pick any other element in the row as coset leader, it does not change the elements in a coset or in a row. The next property is, all the 2k elements in a row or in a coset have the same syndrome. This we can show because each element in a coset are of the form like this, Ej plus Vi H transpose, and since Vi H transpose is 0, they will only depend on the error pattern, and in each row basically it is the same error pattern that appears in the elements of the row. We can again go back to our diagram for standard array and we can see this. You can see in each row, in this row is E3, in this row all these elements have E2. So, they will have the same syndrome. And in the previous lecture we talked about that there are n minus k syndrome equations and n unknowns, and there are total 2k solutions, and you can see here each row has 2k elements and they have the same syndrome. So, these 2k elements are exactly the solution of your syndrome equations, because these 2k elements of a row of a coset, they all have the same syndrome and they correspond to the 2k solutions of the syndrome equations. So, the 2k elements of a coset are actually the solutions of your syndrome equation. And another interesting thing is, each of these cosets or each of this coset leader will have a different syndrome. Why? Because each of these row, if you look at each of these row, each of them corresponds to a different error pattern. Again, let us go back to the diagram that we had for the standard array. This row is related to E2. So, if we compute syndrome for any of these received vectors, we will get syndrome corresponds to E2. This row corresponds to E3, this E4, this one e raised to power 2n minus k. So, if you look at syndrome for each of these rows, they all correspond to each row corresponding to a different syndrome, but within a row the syndrome is same. So, in other words, you can map one syndrome to one row, or you can map one syndrome to one coset. So, this is interesting that now we have one-to-one mapping between each cosets or each coset leader to a syndrome. Another thing to note is, if you look at columns of the standard array, each column of the standard array corresponds to one particular code word. If you recall, when we started the lecture, we said we want to partition our 2n vectors into 2k different sets, and each of these 2k set should corresponds to only one code word, and this is what is happening here as well. You have this whole thing as total possible 2n vectors. Now, we have already partitioned them into 2k different partitions, and these are all distinct partitions. There is no element in here which is common with this element. And another thing to be of interest, if you look at each of these partitions, this partition has all 0 vector, this partition corresponds to V2, this partition corresponds to Vi, this partition corresponds to V2k. So, this is the point basically I am trying to make, that the way we have created the standard array, if you look at the jth column of the standard array, it contains exactly one code word. It corresponds to only one particular code word. Now, if the received code word belongs to column Dj, then R will be decoded as code word Vj. So, whenever R belongs to a set this, we will decode this R as correspond to code word Vj. So, if Vj is our transmitted code word and the error pattern is Ei, and if the received sequence is in false in the column Tj, then we would decode it as Vj, which is correct decoding. We would not make any error. However, if the error pattern is not a coset leader, then R will not be in column Dj, and in that case we will make an error in decoding. So, let us look at an error pattern X caused by a channel, and it is in the lth coset. So, if it is in the lth coset, we are writing this as, let us say this error pattern as EL corresponding to the error pattern EL plus Vi. So, in that case, if we are transmitting code word Vj and we encounter this error pattern, what we would receive is Vj plus X, this would be nothing but EL plus Vi plus Vj. Now, what is Vi plus Vj? Vi plus Vj, sum of two code words, is also a valid code word. Let us call that code word as Vs. So, now the received vector is in partition Ds, and in this case what are we going to decode it as? We are going to decode it as Vs, which is not same as the transmitted code word Vj. So, that is what I meant. If your error pattern is not a coset leader, then R would not be in the same column as Dj. If this would have been coset leader, this would have been just EL, and then receive sequence would have been just EL plus Vj. So, this would have still remained in the partition Dj, and we would not have made a mistake. Okay. So, if the error pattern is not a coset leader, then we are basically going to make an error. So, from this we can conclude that our decoding is going to be correct if and only if our error pattern is a coset leader. And how many such coset leader exist? We have total 2n minus k. So, this we call as correctable error patterns, because whenever our error pattern is a coset leader, we are not going to make a mistake in decoding, and hence we call these as correctable error pattern. Now, the next question to think about is, how should we choose our coset leader? So, clearly our objective is to minimize probability of error. So, the error patterns that are more likely to happen, we should choose them as our error coset leader. And what are those error patterns? These are the error patterns which have least Hamming weight. So, we start with first start with error pattern of Hamming weight 1. If we run out of them, start with Hamming weight 2, 3, like that, because they are more likely error pattern. And we have shown that for a binary symmetric channel, the error pattern with smaller weights are more likely than error pattern with larger Hamming weight. So, among a coset, we should choose the element which has basically the smallest error pattern as our coset leader. And this decoding is basically also maximum likelihood decoding, because we have shown earlier that maximum likelihood rule for binary symmetric channel, it basically chooses V in such a way such that the Hamming distance between R and V is minimized. So, in other words, we have to choose an error pattern that has the minimum Hamming weight. So, that is also the maximum likelihood decoding. So, suppose our received vector is found in the ith column and lth coset of the standard array. So, in that case, because our received vector R is in ith column, we are going to decode it as Vi. Now, our received vector is in ith column and lth coset. So, the error pattern is e raised to power e sub l. So, our received sequence is our transmitted code word plus error pattern. Now, let us try to find out the Hamming distance between our received vector and this code vector Vi, and Hamming distance between received vector and some other code word. So, when we try Hamming distance between received code word R and this code vector Vi, we can see Hamming distance is nothing but number of locations where these two bits are differing. So, if we add R and V and then count the number of ones, that would give us the Hamming distance between R and V. So, Hamming distance between R and V is nothing but Hamming weight of the vector R plus Vi. And what is R? It is EL plus Vi and plus Vi. So, this was nothing but weight of error vector. Next, consider now the Hamming distance between R and any other code word. Let us call it Vj. So, we are finding Hamming distance between R and any other code word Vj. So, that would be given by weight of this vector R plus Vj. So, R is nothing but EL plus Vi plus Vj. Now, Vi plus Vj, sum of two code words is another code word. So, this would be, let us call that code word Vs. So, this will be weight of EL plus Vs. So, what have we done so far? We found out that the Hamming distance between the received code word and this code vector Vi is given by this, and Hamming distance between received code word and any other code word which is not Vi is basically given by this. Now, EL and EL plus Vs are going to be the elements in the same coset, right? And if we choose EL to be our coset leader which has minimum number of ones, then this would be less than this. So, our minimum distance decoding will decide in favor of Vi and not any other code word Vj. So, as I said, since El and El plus Vs are in the same coset and our coset leader has minimum Hamming weight, weight of this is less than equal to weight of this, then this will always happen. In other words, Vi will be closer to R than any other code word Vj to R. So, this will be our correct decoding. So, if we choose our coset leader to be the one which has minimum weight in that coset, the decoding basically based on maximum likelihood decoding will be basically maximum likelihood decoder, because maximum likelihood decoder for binary symmetric channel we have said is the one which minimizes Hamming distance between received code word and the selected code vector V. Okay. So, now to summarize then, how do we do the decoding? We will first compute the syndrome, then each of these syndrome corresponds to one coset leader. So, we find out the coset leader corresponding to each syndrome, and once we find the coset leader, we add that coset leader which is our likely error pattern to our receive sequence, and that would be our estimated code word. And this mapping from syndrome to error pattern basically can be implemented as a table lookup. So, which syndrome corresponds to which coset leader, this can be implemented as a table lookup. Now, we can use this syndrome decoding for both error correction and error detection, and we will give an example to illustrate this. Again, basically as we said, the coset leader corresponding to lowest weight error patterns are essentially used for error correction, and these are the most likely error patterns according to the maximum likelihood rule. Now, we could use this standard array for both a combination of error correction and error detection, and we are going to illustrate this point that we could use a syndrome corresponding to higher weight error pattern for error detection rather than error correction. So, let us take an example to illustrate how we can use this standard array for error correction and error detection. So, this is our 6-3 systematic linear binary code whose generator matrix is given by this and parity check matrix is given by this. These are encoding equations. This is a mapping of the syndrome to the coset leader. So, the first step involved in this is creation of standard array, and I believe now you know how to create a standard array. The first step is the first row of the standard array will be a set of code words. You are already given the generator matrix, so you can generate what are the set of code words. The leftmost entry in the first row, which is the row of code words, should be all 0 code words, and then you can place the other code words in any order. Now, I could not fit in all the columns in one slide, so I have V1 to V4 in this slide, and next I have V5 to V8 in the next slide. Okay. Now, let me explain what I mean by correctable error patterns, detectable error patterns and undetected decoding error. So, out of these all possible error patterns, which are the error patterns that are correctly decodable? Now, if you choose your coset leader to be the one which has the least Hamming weight, which has the least number of ones, and if you make that error pattern as your coset leader, then you can correctly decode those error patterns. So, let us look at each of these rows. Of course, this corresponds to all correct code words. If the error pattern is this, these are the set of other elements of the coset, and you can see here none of these elements have weight less than 2. They are all like 3, 3, 5, 4, and this has weight 4, 2, 2. So, this is the minimum weight error pattern, and this is having weight 1. So, this error pattern is correctable. If this error happens, this can be corrected. What about this? Let us look at other elements. This has 2 ones, 4 ones, 2 ones, 3 ones, 5 ones, 3 ones, 4 ones. So, clearly this has only 1, rest others all have weight 2 or more. So, if this is the error pattern and we make this as coset leader, this is also correctable. Similarly, we can see from other rows also this single error pattern is correctable, this single error pattern is correctable, this is correctable, this is correctable. These are all correctable patterns. So, when I talk about correctable patterns, essentially I mean if you get this, 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 of course, this is no error case, which also I am counting in correctable pattern. So, these 7 patterns, if these are the error patterns, then it is correctable. So, these are the 7 correctable patterns. Now, what happens here? This error pattern has weight 2, this has 3, this has 3, this has 3, oh, this has 2. So, this has 2, this also has 2, this also has 2. So, in this last row, my coset leader is no longer the error pattern with lowest Hamming weight. There are 2 other error patterns which also have Hamming weight 2. Okay. So, in this situation, when my syndrome is pointing to this coset, I would not be able to do error correction. Why? Because I know this could be a likely error pattern, or this could be a likely error pattern, or this could be a likely, and they are all equally likely, because here 2 bits got flipped, here 2 bits got flipped, here 2 bits got flipped. So, any of these 3 patterns are equally likely in this case. So, whenever syndrome points to this coset, I cannot do error correction. However, I can detect error. Why? Whenever it points to this row, I know there is an error because syndrome is non-zero, but I do not know what is my error. So, that is why I call it as detectable error pattern. So, what are those detectable error pattern? This is my detectable error pattern, this is my detectable error pattern, this is my detectable error pattern. Maybe I can use a different this in color. So, I use red, these are my detectable error pattern, these are my detectable error patterns. These are 4 of them, and then remaining 4 are these. So, these are my 8 detectable patterns, error patterns. Now, let us use a different color pen. What about these patterns which have been left out? This, like other error patterns, what happens to them? These error patterns, let us say if this error pattern happens, what is going to happen? If this happens, I am not able to detect these error patterns. Why? Whenever this error pattern happens, this is Hamming weight 3, its coset leader was already Hamming weight 1. So, whenever these error patterns happen, I am not able to detect any of these error patterns. Why? because whenever any of these error patterns happen, I have already taken decision in favor of these coset leaders, because it is less likely to get this error pattern than this. So, these set of 49 error patterns, if any of these error patterns happen, then I am going to make a mistake. This will result in undetected error, because whenever any of these error patterns happen, I would have assumed that the error pattern was this. So, this would result in undetected error probability. So, through this example, essentially I have illustrated how we can use this standard array for error correction and error detection. So, in summary, we would like to make our coset leader as one having minimum Hamming weight, minimum number of ones, and whenever we get an error, our syndrome will be non-zero. The syndrome will point out to a particular coset or a row of the standard array, and we will, if the coset leader has the minimum number of ones, then we will pick that coset leader as our likely error pattern, and we are going to decode it by picking that likely error pattern, adding it to our receive code word, and that would be our estimated code word. So, with this I will conclude this decoding of linear block codes. Thank you.